morning. Last time we were talking about determination of pore size and pore size distribution. So, we were talking about two methods, mercury penetration method and nitrogen adsorption desorption method or isotherm. So, basically BT can be used, whatever P upon V into P 0 minus P, the plot versus P by P 0, you can find out the volume of monolayer coverage. You can determine the area of one molecule of nitrogen, which is 16.2 angstrom square, right, density of the nitrogen, and from that also one can determine the adsorbed layer thickness, what you call T plot, right. So, the adsorbed layer thickness can be calculated by knowing the change in the volume or delta V during the mercury penetration or nitrogen adsorption desorption isotherm. The principle remains the same, right, what we discussed. So, these are the important properties to determine the pore volume and pore size of a catalyst. So, basically I will just talk on nitrogen adsorption desorption method in detail, because mercury penetration method we have already seen. So, how experimentally we determine the pore volume, pore size distribution or thickness of the adsorbed layer. So, these are the basic characteristics of the surface of the solid. So, when a new catalyst is to be prepared or is prepared based on certain preparation methods, maybe co-precipitation or just incipient wetness method. So, you look in terms of the adsorption to look at the chemisorption property, right. So, you need to find out the actual pore size distribution, because the pores are selective for a given catalytic reaction. So, we were just talking last time this nitrogen adsorption desorption method, basically which is based on the principle of capillary condensation, right. So, vapor pressure required to fill a pore. So, lower the smaller the capillary, lower will be the vapor pressure. So, those pores will get filled first and then larger, right. So, that is what the condensation, and when you release the pressure or desorb, then the volume from the larger pore will displace first or remove first. So, you can find out the delta V. So, that is what we are going to look at here in terms of the methodology. So, your nitrogen adsorption desorption method basically gives you the micropore and mesopore. The second one, which is helium mercury method or mercury penetration method, basically a BGH type Barrett-Jordan or a Holland-Applet also can be determined, can be used to determine the pore radius. So, where you see two capillaries, they are dipped in a trough, right. It is a chamber of volume, something definite volume and something like this, and where you have the capillaries dipped in the manometric, that is mercury, right, here like this, and this whole system is under pressure. So, you increase the pressure, right. So, whatever the mercury volume displaces, that will go up, right. So, if you have a known mass of the sample and you apply the pressure, the mercury will start penetrating, right, and whatever the volume of mercury that gets penetrated. So, this will go up, right, or if there is a initially the level. So, mercury which penetrates inside the pore, the level will fall down. So, you can find out what is delta V, right, and then you can correlate delta V with the pressure, and that is what the mercury penetration method can also be used to find out the pore size distribution of the catalyst. So, this is what, but only as I said that based on the surface tension phenomena, right. So, it is used only for the larger pore, 100 angstrom to 1 lakh angstrom, right, not for the meso, because the pores will get cracked. So, principle of mercury penetration method we have already seen, right, the pressure force equal to the surface tension force, and that can be used. So, we have already discussed this. Nitrogen adsorption desorption method, which I was talking, right, earlier also. So, that is the BET method, which can be used to determine the pore size distribution, right. But what I said that by knowing the graph P upon V into P 0 minus P versus P by P 0, which is your BET isotherm, and you can correlate the pressure with the, that is the area of the molecule for a differential pressure, right, and you can get the differential volume of the pore, right, and then you can correlate the adsorbed layer thickness and can find out the pore size distribution. So, same principle is extended here, is that the capillary condensation occurs in the pore and which is based on the Kelvin equation. So, let us look at the Kelvin equation also. So, the method, as I said, the adsorption method of estimating the pore volume and diameter, that is based on the fact that the gas condenses to liquid in a narrow pore at pressure less than the saturated vapor pressure of the adsorbate. So, this is your capillary condensation, right. So, you are applying the pressure, and when vapor pressure is partial pressure equals to vapor pressure. So, either the vaporization will start, if you increase the pressure the condensation will start, right. If you release the pressure it will get vaporized. So, the basic equation which you see in that relation, because it is related to the thermodynamics, right, how much work is being done to increase a drop, because droplet when the condensation is taking place the droplet size is increasing. So, it means between two radii r and r plus delta r, right, there is some change in volume from V to V plus delta V. So, we are looking those differential volumes which is related to applied pressure, right, or when you have a desorption study. So, a larger drop vaporization will take place. So, it would turn to a smaller one, right. So, that is again related to the pressure which is released, right, and that is why we are taking the desorption data there, right, to look at the hysteresis also, adsorption, desorption, hysteresis. So, basically if you look at the work done in enlarging a spherical drop of liquid, and if you equate it with to the work done by in adding the molecule to the interior of the drop. So, there is a change in number of molecules, right. When the volume is increasing you are adding some number of moles of nitrogen on the layer, right, delta n, right. So, these two can be correlated, that is what the Kelvin equation principle, right. So, we are looking our thermodynamics which is related to the chemical potential, right, and this work done, right. So, if you look at this equation, that the work done in enlarging a surface of a drop of liquid is sigma times delta S, right. If surface tension is known, right, which is the force per unit length, right. So, you can very easily find out this multiplied by change in area, right. So, sigma into delta S is the work done in enlarging the surface area of a drop of liquid, where sigma is the surface tension and delta S is the change in surface area, right, of a spherical droplet. So, how will you calculate change in surface area? The area of a spherical droplet is 4 pi r square, right, and when it changes from r to delta r it will become 4 pi r plus delta r whole square, right. So, ultimately the change is 2 pi r delta r into 4, right. So, that is 8 pi r delta r. So, this is the change in the surface area of the sphere when the radii change from r to r plus delta r. So, this is the first thing that what I have written here, that by equating the work done of a spherical droplet to the liquid, right, the first term. Second term is the adding a number of molecules to drop interior, because when the drop is increasing you are increasing the mass of that droplet, right. So, the volume and the change in number of molecules whatever delta n, which is initially r radii is changing r to r plus delta r. So, accordingly the volume is changing from V to V plus delta V, something like that, right. In that we are changing, calculating the change in volume. So, if you know this change in chemical potential, right, mu 0 minus mu. So, mu 0 is when it is a droplet on a bare surface, right, and mu is the on a curved surface. So, you can, if you know what is the change in chemical potential, right, and multiply with the change in number of moles, that is equal to the work done, right. So, when your mu is equal to mu 0, no droplet size or no further condensation will take place, right. So, no, because that is the first thing to have a process, right. So, thermodynamics relation. So, mu 0 is the chemical potential of the vapor over a plain liquid surface, right, that is a wet surface, and mu is the corresponding potential over a curved surface, right. So, between these two you can find out the change in number, that is delta n is the increase in the number of moles of liquid which has changed the volume of the droplet, right. So, related to that was the shape of a droplet, here we are assuming spherical, but it changed from spherical to elliptical, which is related to your principle of thermodynamics, right, because surface tries to maintain its minimum area, right. So, and so that is nothing but related to the thermodynamic, that is change in the chemical potential. So, this equation is written here 8 pi r delta r into sigma, right, which is the work done, right, to create a surface or to create a drop or change in that size is equal to change in the chemical potential multiplied by the delta n, because when it is a plane surface, right, and then when there is a some addition of the molecule, the size or shape will change, curved surface. So, change in the chemical potential of the two, and that is the relationship for the determination of the pore size distribution of pore radius, because we are just looking at how that surface has been created first thing, right, from thermodynamics. And now you can very easily, because the increase in volume of the drop, right, that is nothing but whatever the change in number of moles times whatever the volume, right. In that volume, that is, we are just calculating initial volume and final volume. So, initial volume is your whatever V and changing to V plus delta V, right. In that there is a change in number of moles, right, initially Ni, now Ni plus delta I. So, if you just look at this, this is related to your 4 by 3 pi r cube, right, that is initial volume of the drop, and when it changes to a final size, that will become 4 by 3 pi r plus delta r whole cube, right. If you just expand that term, that will give you whatever the 3 term together, right. So, 3 cancels, which are 4 by 3, and there it will be 3 r square delta r, right. So, that term is r square delta r here, right, and this should be here delta n, correct, change in number of moles. Is that clear? So, volume of the drop which has increased between two successive adsorption in one way, right. So, if I just look at these two equations, right. So, very easily you can this and this. So, I can very easily write the value of mu 0 minus mu in terms of these two numbers, just divide these two equations. So, you have 2 sigma V upon r, where sigma is the surface tension, right, V is the volume of the liquid which is absorbing on the surface, right, and that volume is basically related to your pore volume, right. So, this is how a drop is forming, right, and when there is a desorption, its volume drop will, the size will be decreasing, right. Same thing has been related with thermodynamics, because now you know, because this equation gives you mu 0 minus mu, we have to find out these two values, right. So, let us look at the thermodynamics. So, mu at any standard state, if you know the chemical potential plus R T ln P 0 at that pressure saturation. So, you have the mu 0, right, chemical potential, and at any when the drop forms or the more number of molecules are coming to the surface, its mu is changing. So, that mu is again at a standard state plus R T ln of P depending on the pressure, right, chemical potential relation, mu is equal to mu 0 plus R T ln P. So, at two different pressures. So, you can very easily find out mu minus mu 0 from this equation, right, which is simply R T ln of P by P 0 if I just take mu minus mu 0. So, it means this equation is equivalent to do this. So, that is equal to R T ln P by P 0. So, this is what your Kelvin equation, right. So, a derivation of the Kelvin equation which is related to your thermodynamics principle, right, is here. So, ln of P 0 by P is equal to 2 sigma V upon R R T, where small r is the radius of the capillary, right. So, the only thing what we have discussed earlier, that this is talking the Kelvin radius, because the part of that is the adsorbed layer. Here we are talking the liquid, right, which is vaporizing or condensing. So, once the monolayer has formed, so T is the layer where adsorption is taking place, and after when the pressure increase to a certain pressure, then the condensation phenomena takes place, right, capillary condensation. So, this equation is valid for condensation phenomena, right. So, this equation may be applied to the liquid inside a capillary of circular cross section, because we assume the meniscus as a circular. If the angle of wetting between solid and liquid is alpha or theta, so here it is theta basically, right, that is for nitrogen I told it wets almost all the surfaces. So, right, so the theta is 0 contact angle alpha, then component of the surface tension will become sigma cos of theta, right. So, that we have already discussed, because the principle is same, surface tension force you are relating with the, just like in a mercury penetration method, pressure force, right, and here it is the only thing that this is the condensation phenomena, right, which is related to the chemical potential and change in the size of the droplet. So, this equation here you will have a sigma cos of theta, but since as I said that nitrogen wets almost all the surface. So, its contact angle is 0. So, cos theta becomes 1. So, that is what the here alpha or theta either way can be written. So, ultimately the equation is in general this for any gas on the surface of the solid, right, where cos theta is generally 1, because for most of the wetted surface. So, if you use this equation, I told you that this is based on the capillary condensation phenomena, where so it means the pressure should increase in the capillary, right, a small vapor pressure, and then condensation should take place, right. So, that is the principle here. So, it means this should be used only in the small pore, not in the larger pore, because the larger pore the capillary condensation phenomena will not be valid, right. So, that is the a meniscus has to form, a kind of meniscus when you look at in a capillary type, right, the concave upward or concave downward. So, here it is a wetted surface, so it will be concave downward, right. So, if you look at any principle of that adsorption desorption isotherm, so we have a basically a detector, right. So, this is the detector. You are passing nitrogen through a sample which may be a reference sample here, and that is a reference, and that is your measuring detector, right. So, the gas passes through this. So, generally we use a mixture of nitrogen plus helium, right, and assuming that the helium does not adsorb on the surface. So, it is an most of the time it is an inert material. So, does not adsorb on the most of the solid surface under these conditions, right. So, helium does not adsorb on the surface, nitrogen will adsorb, and that is why you have a here the liquid nitrogen bath, right. So, this will have a temperature of minus 196 degree centigrade, right. So, your gas which is here, and you put your catalyst sample or whose surface area, pore volume or pore size distribution is to be determined, that is the sample is placed here inside the tube. So, this is basically capillary here, right, a small tube, and in that tube you put a known mass of the catalyst sample, and this is just that you have to generate some preliminary data to identify the limit of that pressure, because this surface area, because if the surface area is too high, then there may be error, right. So, generally we set that the total surface area should be in the range of 20 meter square per gram. So, if the sample has a surface area 1200 meter square per gram, then you take a smaller mass of that sample, right. So, the detector it is a limitation of the volume of the gas adsorbed. So, the range should not be more than 20 meter square or 10 meter square like that. So, accordingly you have to adjust the mass of the solid, right, and that you can get from some preliminary data, right. So, you have to take a known mass of the sample which may be 1 gram, which may be 0.1 gram also, right, or 0.05 gram also. So, depending upon the sample area. So, you take that and put it in this, and initially you need say kind of pre-treatment, right. Pre-treatment means evacuation of the pores of the solid, right. So, you have to remove the gases which are inside the pore, you have to remove the moisture from that pore, right. So, you need to give a certain kind of pre-treatment, that is known as pre-treatment of the sample. So, this can be done just by heating the sample in this chamber which is under slight vacuum. So, you can treat the sample, and once that desired conditions have arrived, then you start passing the gas, right, adsorptive gas. So, your sample is adsorbing nitrogen, right. So, when there is nothing is adsorbing, then you will have a constant peak inside. So, if you look at the detector is basically it can be a thermal conductivity detector most of the time, because you are indicating nitrogen, right. So, basically if you look at here, so it is the volume, you will get a peak like this something, right, which is a reference. So, basically suppose if I say that at any time when there is nothing is being adsorbed, all the nitrogen will come out, right, without adsorbing in this chamber, right. So, it means all the gas which comes, and from here it passed through the this reference cell. So, nothing is being adsorbed. So, all the nitrogen will come here, right. But as soon as your adsorption starts, what will happen? The volume of gas will adsorb, part of the nitrogen will adsorb. So, this area is decreasing basically. So, you will get a peak like this, right, and this may decrease continuously, and finally, it comes to the same initial value, right. So, it means the adsorption is complete now, right. So, you can find out these areas or volume, right. So, you can find out what is the volume of the gas which is at your ambient condition is adsorbed, and you convert that volume into the temperature of the liquid nitrogen, which is minus 196 degree centigrade. So, experimentally these all are sophisticated systems where you directly determine or can measure the surface area through using some softwares, right. Or so, but the principle is something like that, that gas is being passed through that and it adsorbs and the volume change is being measured. So, this is what if you have a reference already. So, when nothing is adsorbing, you see a something like a 0, and then when something is adsorbing, it shows a negative, and when you look at a desorption, it is a positive. If you change your reference electrodes plus minus, then the sign may be reversed, right. So, basically this is just saying that this much volume is adsorbed. So, volume of nitrogen is decreased in the exit, right, and when you have the desorption study, now everything will come out from the gas. So, this is the increase in whatever the area from that reference, right. So, this is your reference basically, this guideline G, right. So, that is the principle. So, we can measure the response, which may be in terms of millivolt signals, right, 0 to 1 millivolt and versus time. Same principle will be used for chemisorption also, right. You can use any reactive gas hydrogen and you can find out. So, mercury porosimeter, it can be a kind of BJ's plot which I was discussing. The limitation is that it cannot penetrate small pores or micro pores, but nitrogen can, right. So, that is why this second one, nitrogen adsorption desorption method, is for the smaller pore. Uncertainty of contact angle and surface tension values in for the case of mercury is another problem, right, because mercury does not wet many surfaces, right, most of the solid surfaces it does not wet, right. The angle 140 we take most of the time, but it can vary from 130 to 105. So, you have to use a different method to find out the contact angle like goniometer, right, or so you have to use that first, what is the contact angle for the mercury on that surface, and then so otherwise there will be a kind of uncertainty if you measure that, but for larger pores we are still using this, but there may be some limitation if the angle is not correct. Surface tension also, it depends on the surface mercury and the surface of the solid. So, it may also vary, right, and when you apply this for a high pressure, there may be a cracking of the sample, right, the cracks may form or the sample may deform, right. So, that is another problem because it reaches a high pressure, because under normal condition mercury does not go inside the pore of a capillary. So, you need to apply a pressure, and if the pressure is significantly high, then the pore may crack. This is just a typical sample results which are taken from Thomas and Thomas book heterogeneous catalysis under VCH publisher. So, if you look at here, the one generally in every experiment what we measure the volume of the gas, right, or volume of the liquid if it is mercury penetration method adsorbed, right, per gram of the sample, and this is a function of measured pressure. So, in terms of the megapascal, right. So, 1 megapascal is 10 atmosphere, you know. So, we can very easily use this principle. So, you can see the pore size distribution, and this is the point somewhere where the pores are saturated now, total pore volume, it is a kind of indication of total pore volume. So, this is a cumulative plot which I was talking earlier also, where you have measured the volume of mercury penetrated, right, versus pressure, right. So, the pressure can be say of the order of say 1000 MPa here, right, or 10,000 atmosphere, very high pressure can need to be applied. Similarly, this is the curve for activated carbon. So, you can see that depending upon the type of the sample and their pore size, you have the different kind of behavior here. Here the smaller pressure, because it may be a wider pore here, right. So, the pressure requirement is smaller to fill the all the pore here, something like this, just at if you look at here 9 or 10 MPa all the pores are filled, right, where in this case it can be a kind of alpha alumina. I told you it is a microporous material basically, right. So, requires a very high pressure. And then once you have that, so the first thing is then generate the data, right, the volume as a function of pressure or P by P 0, and then you plot that cumulative plot, and this is nothing but a plot of dV over d of log A, right. You can have a log on that x axis, right, versus the pore diameter. So, sometimes what I told last time also that we plot dV over dA, right, versus pore radius or pressure. So, when your pore radius is increasing like this, it means pressure will go like this, right, or generally we apply pressure like this. So, most of the time you have higher pressure this side. So, it means your pore size is increasing in this side, right. So, this will be P applied pressure and this is your pore size, right. So, then the cumulative is like this, right, and now you have to find out. So, what does this mean? So, this is representing, if I just say this is the cumulative pore volume. So, this is representing the total pore volume of the solid, right, for a given mass. And if you want to see between two pressure differentials or between two radii, so you have to look at this volume, right. So, a slope can be measured delta V upon delta A, right. Since A is a small number, so you can take a log of that, dV upon du log of A, right, and you can plot another graph, and that will give you a kind of pore size distribution like this. So, this is known as pore size distribution, which is dV over dA, that is delta V upon delta A versus A measured from the tangent, right, or you can just plot a log of that semi log dV over d of log A versus this. So, this is known as a pore size distribution. So, this what does it indicate? It indicates that the most of the pores or all the pores in the solid are between 100 and 1000 nanometer, right. So, this is the indication of that, and these are the kind of pores which have the maximum number of pores are of this size, right. So, that is the meaning of distribution, right. But you see when you do the sieving, then also you have this kind of distribution, and you call it that differential and cumulative methods of analysis for determination of particle size, right. So, this is the indication of the pores available in a solid. So, the pores size distribution may be like this also, bimodal, multimodal. So, these are just indicating the different kinds of pores available in one solid, right. Micropore, mesopore and macropore, all type of pores are available. This is the right the distribution of the pore size distribution. So, this depending upon the type of solid, the pore size distribution may be different. So, this may be a case of your alpha alumina, and this may be a case of something like carbon, where the surface area is very high, right, a wide pore size distribution. So, basically the determination of total pore size distribution, we have now already understood about that, and the principal steps which, because in between to find out we can have the intermediate properties also, just like T plot I said, right, thickness of the adsorb layer, thickness of the mono layer. So, that is also equally important to characterize a surface, right. So, the principal equations we have already seen, right. So, the whatever you need to find out the thickness of the mono layer or multilayer which is formed, right, the pores radius. So, R, that is R p is related to your thickness of the plot plus this, right. This is your whatever the equation, Kelvin equation, and plus the thickness of the adsorb plot. So, that is your total pore radius. So, instead of this is like that, right, and you have the Wheeler model also. So, by which one can determine the thickness of this T, right. So, this is a Wheeler model. So, I will come back to that again. So, in experiment what we are doing, the amount of nitrogen adsorbed at equilibrium, right, at the normal boiling point, which is for nitrogen roughly minus 196 degree centigrade, that is measured over a wide range of nitrogen partial pressure, right, and that is below atmosphere. So, saturation pressure of nitrogen, right, 750 millimeter of mercury. So, and then you identify the amount required to cover the entire surface by a monolayer, Tm, right. So, that is what we were talking for nitrogen, what is the value of Tm monolayer thickness, that can be determined if you know the area of one molecule and then total volume of the gas adsorbed, and at a standard condition 1 gram mole of the nitrogen has how much volume. So, by using this gas law you can calculate, and knowing the density of the liquid nitrogen, one can determine the thickness of the adsorbed layer, assuming that they have some hexagonal closed pack array, right, because molecules are adsorbing on the surface, right, and we have to give that when a monolayer form, these are the number of molecules, area of one molecule is known. So, mass of that molecule can be determined, right. So, per molecule how many per unit mass how many molecules have adsorbed, you can find out, and then determine from the thickness of one layer. So, you can find out. So, we have already seen this, that P by P 0 less than 0.1, we say that a monolayer is formed, right, which is just indication of this here, and 0.1 to 0.4 it is a multilayer adsorption, which is here like this, right. This is the multilayer adsorption, and when it goes more than this, then the capillary condensation phenomenon takes place, right. So, that typical BET isotherm curve, if you look at that, when you apply the pressure. So, generally we do not go more than P by P 0.3 or right. So, even less. because we know we can understand that up to that the monolayer has formed, right, and that those data are sufficient to give you the total surface area of the solid. But when you want to do the pore size distribution, right, then you need to go to a higher pressure, right. So, you may have 7.4 points, you need more than 7 points, because that time you need to go to a larger number of data point, right. In the same range also you have the 3 point, 5 point, 7 point, even in the monolayer, that is in this zone, to get the more and more accuracy of the data, right. But it is advisable that when you look at a complete pore size distribution, you go with a wider range of the pressure, because that is related to the capillary condensation phenomena, not the adsorption phenomena, right. So, this is only if you go p by p 0 less than 0.1. So, you will get just a monolayer, and that is sufficient for determination of total surface area, right, or average radius of the pore. So, that is what written here by BJ's method, the pore size distribution of the catalyst is characterized, that is BJ is Barrett, Joyner and Hollanda, right. These three scientists, they have developed this method, and basically it is a T plot method, where when you look at the adsorbed layer thickness and then you can calculate. So, we will just look at those steps, right. So, related to Kelvin equation, right. So, in this we have already seen this earlier also. So, I am talking about this 0.354 nanometer or 3.54 angstrom is the monolayer. When the monolayer forms, that is the thickness of the nitrogen, adsorbed layer nitrogen for a monolayer. So, I was talking last time the total layer thickness T is your total thickness, right, and that is equal to, if you know that the number of layers how many formed, right, and what is the thickness of one monolayer Tm. So, that is the, and number of layers you can go with the BET isotherm, because it is a multi layer, right. So, you have to calculate the total number of molecules or mass, right, of the nitrogen adsorbed or volume of the nitrogen adsorbed, and then you calculate the surface area or volume, right, for a monolayer and related with the thickness. So, that is what we are looking now, that we have already said this, that BET is only valid for small pressure intervals. You need to give the pressure differentials, right, for say smaller pressure differential, the results will be better, and interpretation may have some problem. So, that is what the BET, because otherwise this T, the BET can also give you the thickness of the adsorbed layer, that is what I said, right, earlier, the volume of the gas adsorbed and you correlate. So, but that is not a very correct method. So, that is why nitrogen adsorption desorption method is better, right. So, we are looking that. So, plot of this thickness T of the adsorbed layer can be calculated, right, that is what we have seen earlier. The Wheeler's model is one, right. So, that is based on the Kelvin equation itself, right, and this what we are talking is that in general you have the layers which are forming like this, and we are interested in this kind of monolayer thickness. So, if you know the T from BET equation, as I said, right, just the volume of the gas adsorbed, in that volume how many mass is adsorbed, and if this one monolayer form, this is the thickness. So, how many what is the multilayer thickness, that is T, right, as a function of pressure, because that is a function of pressure, right. So, if you plot T versus P for any non-porous material, that is same, and that has been checked experimentally, because there only monolayer will form, no capillary condensation, right. So, generally to have our base, we select a non-porous material and then calculate this 0.354 what I have said, right. There no multilayer will form, but once you have a porous material, then the multilayer condensation will take place, and condensation will give you the multilayer thickness, right. So, this helps you to interpret that how many layers are formed, and when the actual reaction is taking place, what number of layers may form, or when you look at the surface area or determine the metal surface area or dispersion, that is also related to the thickness of the adsorbed layer. So, this equation I am showing again and again, because these equations are related. The first thing is that Kelvin equation, which is related to the vapor pressure, right, to fill a pore of a capillary, right. So, RK I have written here, which is now Kelvin radius. So, because this is not the total layer or total related to the pore volume, rather it is only the thickness which is above that. So, if I talk this layers, this is adsorbed layer. So, after that the equation will come. So, that we have already seen, and just a quick look I am just talking. Suppose this is the capillary. So, now as I said that part of the layers are adsorbed. So, they will not be available for condensation. So, this layer thickness is adsorbed layer, right, and now this is the surface where the condensation and vaporization will take place on this. So, what we are getting from Kelvin equation, because that is talking the vapor pressure of these layers, right. So, this is your RK basically from this side to this side, center to this, whereas the total pore radius is your RP, correct. So, and this delta V is the nothing but the volume of gas which is adsorbed for making adsorbed layer, right. And here the whatever the vaporization takes place, that will give you the idea that the volume of the pore which have been vacated because of the capillary desorption phenomenon, right, because it is related to the vapor pressure and vapor pressure is related to Kelvin equation, right. So, not for this adsorbed layer. So, that is the first part here, that the Kelvin equation which we have written here in this. So, that is your Kelvin radius RK. So, actual pore radius will be this what you get from here plus the thickness of that adsorbed layer, right. So, this is your RK which is calculated from this and this, and thickness of the adsorbed layer as I said BET method, or you use this Wheeler model, right. So, this is again given to the power 1 by n. So, roughly n is 3, right, correct. So, this can be used to determine the thickness of the adsorbed layer, and that is a function of pressure. So, you can find out T as a function of pressure as I said in the BGH method also. So, let us see that. So, there are several steps, and these steps I have taken from the Thomas and Thomas, right. So, this is given in chapter 4. So, basically what we have now, we have the data something in this form. Experimentally you are having this data. If you just carry out a lab experiment without using any software, then you are basically determining the volume of the gas adsorbed, right, under normal condition, right, as a function of pressure, differential pressure, right, one condition in this setup. So, we have this data, and now what we need to find out? We need to find out Kelvin radius, right, we need to find out adsorbed layer thickness, we need to find out the change in volume between two successive pressure differential, right, volume desorbed, and then we need to find out pore radius, right, that is the pore size distribution, and then we can find out the thickness or delta of that thickness between two change, that how the adsorbed layer thickness decrease when the pressure is applied, right, or increase when the pressure is applied, right, because when you are applying the pressure the thickness is changing, right. And then you have the change in volume in the between two successive pressure differentials, right. So, likewise what I mean to say, then you can find out the Kelvin, that is the volume differentials between two radii r and r plus delta r, surface area, change in pore volume. So, plenty of information can be obtained from that P by P 0 versus volume. So, these are the steps which I have shown here. So, the first point is that from P by P 0 versus V, right. So, you have plotted that cumulative graph in one way, right, and simplest as I told you, you are calculating dV over d of log A, that is your pore size distribution, right, graphically, right. If you look at the software algorithm, it goes like this. So, just compute the Kelvin radius RK, which is an angstrom unit, and that is from the equation which we have already talked here, right. So, your RK is calculated. Surface tension is known to you for nitrogen 8.85 into 10 to the minus 5 Newton per centimeter, molar volume, that is in the unit of centimeter cube per gram mole, right, you know 1 gram mole of the gas, right, which has 22.4 liter. So, for nitrogen you can very easily calculate the volume per gram mole. So, roughly comes 34.6 or 35 centimeter cube per gram mole, right. So, RK is in simplified way is calculated like this, right. So, Kelvin radius is simply 9.53 divided by P 0 by P, where P 0 is the saturation pressure, right, and P is the pressure, applied pressure. So, at different pressures you will have different value of Kelvin radius, that is the first term, and this is shown in the table, but I have shown you. Once this is known, second point is compute the adsorbed layer thickness T from equation 11 here. So, this is the thickness of the adsorb layer, right. So, the algorithm is now provided and you can directly, your software is there and your system like Micromeritics, you get directly these values, right. But one has to understand these things, that how these value came, right, or if you want to develop your own code, you can use these algorithms, right. So, this is the thickness of the adsorb layer. So, once this is known, you calculate the decrement in the adsorb volume, because when there is a vaporization, the volume is decreasing, which I have talked earlier, right, related V and V plus delta V and related to the radius, right, 4 by 3 pi r cube of a sphere, right. So, change 4 by 3 pi r plus r whole cube, right. So, you can very easily calculate from this by finding the difference between the successive values in column 2 and that has been shown in column 5. So, basically what I am showing here in this is the decrement in the adsorb volume. So, let me show you that table first, this one, right. So, this is the change in the volume. If you look at this value and this value, so between two successive pressures. So, basically this curve is used to calculate that when you have changed the pressure from P to P plus delta P, what is the change difference in volume. So, when at this pressure the volume adsorb was this, right, and when the pressure change, this is representing a, if I go from here to here, it is a cumulative volume basically, right. So, this 125 and 131, so difference of this minus this is reported here, this, right. Same thing for the this minus this will be reported here, right. So, this indicates simply the successive difference, right, in volume of the gas which is vaporized between two successive pressure. If I have adsorption, then this will increase in this way, right. If I have desorption, then it will decrease in this way, right. So, this is reported in column 5 as I discussed, and then you calculate the corresponding pore radius from R p is equal to R k plus T, because now adsorb layer thickness is known, R k you have already calculated. So, pore radius can be determined, right. So, R p is equal to R k plus T and that has been shown again in the column. So, I will go back there later. Once this is known, so I told you that I want in delta T, that between two successive pressures a differential volume has been vaporized or reduced, right, changed, and between, so when these two volume change, how much thickness of the layer is decreasing or increasing, right, when it is adsorption increasing, desorption decreasing, right. So, that is the delta T which the adsorb layer is thinned, right, when it is a desorption. The following a decrement in the amount adsorbed is found from successive values in column 4. So, that is what here, this is your column 4, right. So, if I just take a differential between these two 14.2 and this, so that has been shown here 7, right. So, that is when the pressure was this, the thickness at this pressure 0.960. So, I am talking 0.914, the thickness was 16.4 angstrom, right, and when you change it to pressure 0.871 desorption. So, reduce the pressure to this, the thickness changed to 14.2, right. So, what is the thickness which is changed between these two is 16.4 minus 14.2 and that value has been reported here and so on. So, you can get the idea that what pressure there is maximum vaporization or maximum release of the number of molecules or what is the distribution, because the thickness of the adsorb layer is related to the capillary size, right. So, you can get the idea about the capillary or you can have the idea about the hysteresis also, that is adsorption desorption hysteresis which is related to this, right, delta T of the adsorb layer thickness or the pressure differential. So, this is done and now compute the change in volume or decrease in the gas volume delta V f by which the adsorb film has diminished during each desorption step. So, now we are talking that what is the volume change, right, from two pressure differentials, right, and that is related to in terms of the adsorb layer thickness also. So, this is a different approach basically, because we are saying that the quantity is calculated from the volume of nitrogen which is measured at a standard condition of temperature and pressure to occupy 1 meter square of the area of the surface, that is 0.23 centimeter cube. If you calculate from your PV is equal to nRT, then 1 meter square, because 16.2 angstrom square is the area of one molecule of nitrogen, right, and 35 centimeter cube per gram mole also I have talked. So, one can very easily calculate that if you have the 1 meter square of the surface and nitrogen has a surface area of 16.2 angstrom square, right. So, how much volume of that gas, right, will come to that at a density of 0.808. So, that comes roughly 0.23 centimeter cube, right, if you calculate that. And so, now we are interested in calculating the height of single hexagonal layer, right. Height of a single hexagonal, we are assuming that the nitrogen molecule that adsorbs on the surface are arranged in a array, right. So, one over other stacked. So, if you know this, that what is the mass of nitrogen in hexagonal pack, right, and you know the area mass of the nitrogen in the hexagonal pack per unit area, which can be determined, right, because you know this is 16.2 angstrom square, that volume is known, molecular weight of nitrogen is known. So, this thickness, basically it is the thickness or height of a single layer I am calculating T, right. So, which is I have already shown earlier also, right, 3.54, the same thing here. So, we have written it 3.6 angstrom. So, basically hexagonal pack per unit area mass of nitrogen and density is known 0.808. So, multiply these two, if you get, so you can have the value of the nitrogen thickness. So, that is basically this number which I was talking, right, and can be calculated if you have a non-porous material also, but basic idea is that what is the mass of the nitrogen molecule which adsorb, what is the thickness of that layer is to be calculated, height of one mono layer, right. So, and that is nothing but calculating that 16.2 angstrom square is the area covered by one molecule of nitrogen. So, in that molecule, what is the mass of that molecule is m by n0 rho, right. So, that is what earlier I calculated, r is equal to m by n0 rho to the power 2 by 3 radius of that molecule, nitrogen radius, right. So, that is related to this. So, if you know that, which we are saying that this is roughly 3.6 angstrom. So, you can calculate the required quantity in the units of delta V f. So, what is delta V f? You just try to understand again, decrement in the gas volume, right, by which the adsorbed film has diminished, right. So, it means what we are talking, there is a thickness, right, and when the, so when there is a, so I am saying this is the adsorbed layer thickness. So, in the, if this thickness has changed by this delta T, right. So, what is the volume has gone, what volume of the gas has been or liquid has been vaporized, because it is the condensed layer, when you have released the pressure. So, part of the volume has vaporized. So, in that what thickness delta T we already calculated, because that is something which is related to basically 4 by 3 pi r plus delta r whole cube minus 4 by 3 pi r cube, which I was talking earlier, right. It is related to volume also, because the volume of the gas molecule is decreasing, size is decreasing, right. So, that layer thickness which we are correlating, because you know this now, right. So, that is the change in thickness. So, this delta T has been removed. So, in that delta T, and this is when the per layer thickness, right, basically one thickness. So, 0.23 is this which we have written here, that the volume of nitrogen per meter square has this much volume, right, per unit area, and so per unit area has this is the thickness of one layer and this is the change in thickness, right, delta T. So, it means, and this is the surface area, and one area SR is the total accumulated surface area which is given here, right. So, surface area multiplied by thickness, right, that is something related to a kind of volume, right, and this is what I am saying, the per thickness, right, when the per unit this 3.6 angstrom is the height of the single layer, which is thickness basically, right. So, in one way you can calculate that change in thickness delta T when the or number of molecules in that delta T divided by, if I take thickness of this. So, it is talking in terms of number of layers basically roughly, right, and in one layer what is the area I am calculating, right. So, I have calculated the number of areas here, right, number of layers which has some area, and 0.23 I told is the mass per meter square. So, in that meter square what is the area, right. So, this delta T upon T is talking number of layer, SR is talking area. So, in the per layer. So, this SR into delta T is talking the total area of those layers, right, and in meter square what we have talked earlier, and this 0.23 is per meter square. So, multiplied by that. So, this is simply representing the change in the volume of the gas which has decreased from the surface, right. So, SR I will just look at this thing delta Vf, right, which is related to the change in number of molecule, because you know delta T here, thickness of this, you have already calculated this, right. So, this change in thickness, and when you see that the per molecule I have talked that 3.6 angstrom, the when they are arranged in the hexagonal pack, the thickness or height of that layer at job layer, right, and this is the thickness. So, if I just take 2.2 change in thickness divide by 3.6, it is talking something change in number of layers or thickness of that layer. And now, I am interested in this thickness of the layer, right, what is the area decrement delta A, right. So, I know that 0.23 per meter square. So, I just calculated the area decrement, right, and multiplied it with the total which is here SR. So, that is gone here basically this one, right, meter square per gram for that given change in volume for the surface. So, multiply that. So, that will give you the total surface area, right, which is, and in that given volume which is 0.23 per. So, the total volume of that decrement can be calculated. So, what I mean to say here, although this is not a very useful information, but this can give you the volume of the gas which is dissolved in a given differential pore size. So, if the pores are wider, right, the drop will be faster in that range, and when the pores are narrower, the volume drop delta Vf will be smaller in number. So, you can get the idea that which kind of pores are dominating in your system or in your catalyst. So, that is the important property which you or information which you can get from this information, but only for a differential size. So, this can be used when delta F is known, you can find out the Kelvin ray volume also, because see now we have calculated the dissolved layer volume, right. This is not the capillary condensation phenomena, right, and so that is why we calculated it from our surface area method of measurement. SR is the surface area of the adsorbed layer, right, 16.2 angstrom is the one molecule, and then we have calculated the total, right. So, if this is known, which is the volume of the adsorbed gas, right, adsorbed not the condensate. So, total volume is already known, pore volume, right, minus this adsorbed is your Kelvin volume, which can also be correlated with pi r square L, right. That is something like equal, this is nothing but equal to that one. If I just calculate pi r square L and the same thing again at pi r plus delta r square L. So, you are calculating 2 pi r delta r, that is the surface area, right. Oh sorry, that 2 pi r delta r into L is the volume, right, volume of the capillary condensate. This is your R k, right. So, if you know the Kelvin radius and you know the length of the capillary, so pi r square L is the volume of this, right, and from there the desorption is taking place. So, when desorption is taking place, your R k is changing, right, that is what we have seen, right. So, desorption taking place means R k is decreasing, right. So, more some volume has gone. So, from this what is the volume left is your delta V k, right, between two Kelvin radius R k and R k plus delta k. But this term which I have talked delta V f is there for the adsorbed layer. So, this delta V f is the volume of the gas which has dissolved from the adsorbed surface, right. So, basically we are not talking that part, because that we have calculated from our BET isotherm or for a pressure P by P 0, right, because we know the T for that adsorbed layer or mono layer what 0.354 nanometer we said, right, and then we know that this 16.2 angstrom is this area. So, between two successive layers we are calculating what is the change in number of adsorbed molecules, because that is a monolayer and when multilayer forms then there is a change, after that condensation. So, you can find out the volume V k delta V k which is attributed to the desorption from the pores containing liquid condensate rather than the adsorbed gas film. So, just make this difference. The adsorbed layer has the gas film, right, and after that the condensation. So, that this is your basically your adsorbed gas, right, and that is why we have used those surface area, we have used the thickness change, right, of that is above R k, right, delta T within that monolayer, and then we calculated delta T, right. So, that we are calculating. So, you know this relationship as I said here pi r square. So, for a hypothetical cylindrical capillary, if you know, right, elementary geometry shows that the relationship between volume decrement delta V k corresponding to the Kelvin radius is related to this. So, delta V p divided by delta V k is equal to R p divided by R k whole square, right. So, pi r square L is the volume of the Kelvin radius pore and pi r p square L is the volume of the total pore. So, you can find out the change in volumes of the pore, that is total pore volume divided by the Kelvin radius pore volume, and that is related to the radius of the pore and radius of the Kelvin radius. So, this also we have already discussed that the specific surface area delta S corresponding to a delta V p volume contained by a cylindrical capillary is 2 delta V by R. So, that also we have discussed last time, 2 times V g by S g is your R bar, right. So, last time if you remember R bar average pore radius is 2 times V g divided by S g, right, where V g is the pore volume, S g is the surface area BET area. So, here S g is calculated which is 2 times V g divided by R radius of the pore, right. So, if I just talk for two differentials, delta V is the volume change, right. So, and delta S is the surface change. So, we can very easily correlate it in terms of the change in the pore volume, right. Delta V p and R p are correlated with respect to the specific surface area, right. So, pi r square L is the volume of one pore, right, and 2 pi r L is the surface area of that pore. So, you can, so S j is 2 pi r L for one pore, pi r square L is the V for one pore volume. So, if you divide these two, you will find R which is 2 times V by S, right. So, S is 2 times V by R. So, that is known to you, but since there is a quantity delta V p which is reported in centimeter cube per gram of the gas at STP rather than actual volume of liquid condensate, it is corrected by multiplying the ratio of gas to liquid density rho by rho L. So, you can convert very easily at one condition of temperature and pressure to the liquid condensate temperature, because the condensation is at minus 196 degree centigrade, whereas the gas volume which you are calculating is at standard condition of temperature and pressure, right. So, by using P v is equal to nRT or P 1 V 1 over T 1 is equal to P 2 V 2 over T 2. So, that will be simply a ratio of the density of the gas divided by the density of the liquid. So, liquid nitrogen density I said roughly 0.8, right, gram per centimeter cube, gas density you can calculate P upon R T, right. So, the order of magnitude comes roughly 1.6 into 10 of minus 3 for the case of nitrogen, right. So, you can very easily correct it the volume. So, delta S is which is equal to 2 times delta V p by R p in general, and this is calculated at standard condition this, right. So, 1.5 into 10 of minus 3 change. This 10 to 4 has been introduced. So, because there is a difference between this is in centimeter cube per gram and this is in angstrom unit, right. So, just to take care of this. So, V is in centimeter cube per gram, most of the time pore volume we report in centimeter cube per gram and radius is reported in angstrom. So, just to take care of that, so factor 10 of 4 will come in picture, right. So, that is the factor, and this is, so roughly it is 31.16 or 31.2 delta V p upon R. So, this is the surface area between two differential pressures, right. The number of molecules, surface area is related to the number of molecules of the nitrogen adsorbed on the surface, right. So, when there is a desorption, the number of molecules are released, right. So, how many molecules have released from the surface. So, that is related to the decrease in the surface area in that way. So, the total accumulated surface area S r in column 12 is sum of the value of column 11 and is employed in column to calculate column 8. So, basically just add all these delta S. So, that is should be equal to the total surface area BET surface area, right, because these are nothing but decrement in surface area of the catalyst, right. So, total accumulated surface area S r in column 12 is the summed value of column 11 and is employed to calculate column 8, right. So, that we have already seen. So, this is known. So, calculated delta V p in column 10 centimeter cube per gram of nitrogen. So, you convert it into any other convenient pressure. So, you can have the correction factor again for the density, right. Actual volume of liquid filling the pore, right. So, that is again multiplied by the density of the gas to the density of liquid. Now, this is just a conversion factor, right. So, final column gives the percentage of volume contained by the pore of radius greater than the pore radius R p from column C. So, that is a cumulative change, right, or between two radius R and R plus delta p, what is the change in the volume percent of the pore, right. So, that may be equal to nothing but change in volume divided by total volume and multiply in the terms of percentage, right. So, I stop here.